Good afternoon, everyone. We are here for the third session for today. Today we have Dr. Ajit Kumar. My voice is audible? Dr. Ajit Kumar have joined.
Sir, yes, sir. I can hear you.
Okay. Thank you. Okay, Dr. Ajit, I welcome you in this sixth session of our FDP. Uh, so Before Dr. Ajit will share his presentation, I just briefly introduce Dr. Ajit Kumar. Presently, he is an associate with the Department of Mechanical and Aerospace Engineering at IITRAM, Ahmedabad. Before joining IITRAM, he worked as a DLR DART postdoc research in the Institute of Flight System in Germany Aerospace Center DLR. He received his PhD in aerospace engineering from Indian Institute of Technology, Kanpur in 2019, Master in Instrumentation Engineering from the Madras Institute of Technology, Chennai, and Bachelor's from the Electronics and Instrumentation from West Bengal University of Technology, Kolkata. He has also worked as a research assistant in the Department of Aerospace Engineering, ISC Bangalore, and CSIR NAL Bangalore in 2012 to 14. His research interests include the machine learning-based fixed-wing aircraft and rotorcraft identification, UAV, and the experimental flight mechanics. Dr. Ajit, we welcome you. Please share your presentation and please start. Thank you, Dr. Ajit.
Thank you, sir. Thank you for your introduction, and I'll share the screen now. Is it visible now, my screen?
Yes, sir.
Sir, screen is visible now?
Yeah, Dr. Ajit, it's visible.
Okay,
Please
perfect.
go ahead, please.
Okay, thank you. So the topic for this session's presentation is aerodynamic parameter estimation using flight test data. And in this presentation, I would be talking about the introduction part. I mean, what this problem is about, what is aerodynamic parameter estimation using flight test data. And then we will also talk about problem formulation in this. And once we formulate the problem, then I'll discuss about the methods to solve this problem of parameter estimation. And then we will discuss the results followed by future directions of this work. So before I start the work, I would like to introduce with the terms which I said estimation here, parameter estimation. So let us try to understand what parameter estimation is about and where it fits in system theory. So we all know in system theories, we have three different components. They are well known as control system, simulation, and identification. So these three terms or the concept, they deal with these three entities, and they are, you can see in the screen, it's the input, output, and the system. So whatever we are saying about control, simulation, and identification, they will be related to these three entities. So when we have the knowledge about the system and also the knowledge about the output, I mean desired output, what we want to achieve, then this is a problem of control system. So here it is control system. And in other case, when we have input data or input, the knowledge about the input and also the system, and we are trying to study the performance of the system, or we are trying to know the output of the system, this is an explanation for simulation. And the third thing, it's quite interesting. Sometimes what happens, we know the input data, we also know the output data from the system, but we are not sure about the mathematical behavior of the system or what the system is about. So when we have these two data set, input data set and output data set, then the problem falls under the category of identification. So this was the quick introduction on identification. Now there's parameter estimation. So parameter estimation is a subset of system identification, and as I said, system identification is a determination of mathematical model from observed input and output data set. So in this example, you can see we have an aircraft, which is essentially Hansa 3 from Flight Laboratory IIT Kanpur. And now you can see this is the, just for the reference, I have put input data and output data. So input variables contain alpha, which is your angle of attack, pitch rate, normalized pitch rate, and elevator angle. And for output, I kept CL and CM, which is your lift coefficient and pitching moment coefficient. So just to give interpretation, we have, let's say, these two data set, and we want to find the behavior of this aircraft, precisely behavior of longitudinal dynamics of the aircraft. Then this is known as parameter. This is known as system identification. And when the model is structured in terms of parameters, then finding those parameters will be a problem of parameter estimation. So now coming to what is aerodynamic modeling and parameters. As I said in the title, it is about finding aerodynamic parameters. So as we know, a very standard representation of aircraft in 6 degrees of freedom, we have seen terms appearing in the equations are CL, CD, CM. I will also elaborate in subsequent slides. So just to give you the introduction, CL is lift force coefficient, CD is your drag force coefficient, and CM is your pitching moment coefficient. And in the lateral directional part, we have CL, CY, and CN. They are function of side slip angle, aileron, rudder, P and R. So they also have the standard meaning. So for example, CY is your side force coefficient, rolling moment coefficient, and CN is your yawing moment coefficient. So we will see in detail, just to give you the introduction, what we refer when I say aerodynamic parameters. Okay. So now, after introducing, we also want to know why parameter estimation is required, why we are going for aerodynamic modeling and parameter estimation. So these are the motivation of this work, that we always have a need and quest for better understanding of aircraft. So aircraft can be a manned or unmanned, it can be fixed wing aircraft, it can be rotor wing aircraft or multi-rotor aircraft. So anything, any aerial vehicle can come in this category. And we also know the importance of deriving flight dynamic model, because it helps in investigation of system performance and stability characteristics. It helps in finding high fidelity, high bandwidth model for in-flight simulators. It helps in designing a good flight control system. It also helps in doing analysis on handling qualities compliance. Apart from these advantages, we also have an advantage of finding aerodynamic database with the help of aerodynamic parameters. And we also validate design parameters, for example, wind tunnel parameters, using these parameters. It is also useful in finding fault and diagnosis, of course. So these are the motivations of doing parameter estimation related stuff. Now coming to problem formulation, how exactly we formulate this problem. So as I said earlier, we have standard representation of aircraft dynamics, and generally we assume that the dynamics in two parts are decoupled. They are longitudinal dynamics and lateral directional dynamics. So the equation for longitudinal dynamics are here, and the variables which are appearing in the screen, they are V, alpha, theta, and Q. So V, standard representation of V is airspeed, alpha is your angle of attack, theta is your Euler angle, pitch angle, or Q is your pitch rate. So I have highlighted these three terms, as you can see, CD, CL, and CN. So they are your force and moment coefficient. So for example, CD is your drag force coefficient, CL is your lift force coefficient, and CM is your pitching moment coefficient. So I'm sure you will be knowing the physical representation and understanding also you will have about these force and moment coefficients. So, and other terms also have the standard representation. So it's written here. So for example, Q is your pitch rate, wing area, mass, angle of attack, pitch angle, inclination angle of engines, thrust, dynamic pressure, elevator deflection, wing chord, moment of inertia, and density of air. So similarly, and also when I was showing you these coefficients there, CD, CL, and CM, we have sort of assumptions on these that they vary linearly with respect to angle of attack, elevator, and pitch rates. So CD, of course, it will not have much effect by pitch rate. So this model is simply dependent on alpha and delta E. So this is also a linear representation. We assume that our flight test data has been gathered in the linear regime. When I say linear regime, it says that your alpha should be low and essentially lower than 5 degree, or it should be in between 2 to 3, right? So when aircraft is flying at lower angle of attack, then this model is still valid. So we are taking here a linear model here for CD, CL, and CM. So now as you can see, CD equals to, for example, is CD naught plus CD alpha plus CD delta E. And terms in CL, CL naught, CL alpha, CL delta E, and CLQ, and terms in CM, CM naught, CM alpha, CM delta E, and CMQ, they are essentially known as aerodynamic parameters. And these parameters also play a very important role in characterizing the aircraft, as I said. So that's why it also has to do something with the stability and control analysis of the aircraft. For example, when we have the number of CL alpha, we can comment on the stability of the aircraft. When we have the number, let's say CM delta E, we can comment on the controllability of the aircraft. So the variable or the parameter which is related to your elevator or control surface, they help in characterizing control aspects of the flight vehicle, and other parameters like CL alpha and CD alpha, CM alpha, they talk about stability performance of the aircraft. So we will learn these things throughout this present slides. So similarly, as I discussed about longitudinal dynamics, so similarly we have lateral and directional dynamics, in which variables or state variables are beta, which is your side slip angle, P dot roll rate, or P is essentially roll rate, P dot will be rate of that, and R is your yaw rate, and these are the Euler angles, phi and psi. Okay, and in these equations also you can see the variables appearing like Cy, Cl, and Cn. They represent lateral directional force and moments, and their notations are nx is acceleration along x direction, nz is acceleration along z direction, phi is your roll angle, and y, f, l, e, and g, these are the engine parameters, and beta is your side slip angle, r is your yaw rate, p is roll rate, p is wingspan, and delta r, delta a, they are control surface deflection, rudder, and aileron deflection. So here Cy, Cl, and Cn are called as coefficient of the side force coefficient, and rolling moment coefficient, and yawing moment coefficient. So again, we assume that the relationship between force and moment parameters are linear with respect to flight variables like beta, r, p, delta r, and delta e. So that's why we got again a linear equation. So now, problem for lateral directional dynamics could be finding these parameters: Cy naught, Cy beta, Cy r, Cy p, Cy delta r, Cy delta a, etc. Similarly for Cl and Cn. So I hope now we are clear with the problem formulation part. Now immediately these questions will come in mind, that when we have described about the problem, we know about the problem formulation of the system, then how to solve them, how to find these aerodynamic parameters. So we have different approaches to solve this problem. First one is analytical method. So under this method, when we have the details about the aircraft, means we know the geometry of the aircraft, then we can get first cut idea on aerodynamic parameters. So this is one of the simplest and required methods to do this analysis. And second one is wind tunnel test method, which is also quite popular. In this, usually we scale down the aircraft, whatever aircraft it is. Suppose it's unmanned aerial vehicle of small size, then we can put full scale model. And after inserting inside the wind tunnel, then also we can derive these aerodynamic parameters. So this is the second approach by which we can get wind tunnel, aerodynamic parameters using this. And third one is flight test data. I mean, in this method, we have to fly the craft or the UAV if we have, and then we have to gather the data, and then we can do parameter estimation. So why these three different? Because as we know, it's one of the simplest method, I mean analytical method, and it has a lot of constraints because we have a lot of assumptions on finding the parameters. So it's not very well suited when we go for design of control system and simulator, but it gives you the first cut idea on the aerodynamic parameters. It will not be very accurate because of its on constraint. Again, in wind tunnel test, we have certain issues like boundary effect and scaling effect, and also it's very hard to emulate everything what happens in atmosphere. So the test data which we get from wind tunnel also will not be very accurate because of such constraints. So we have this third choice of flight test data method by which, because everything is we are dealing with the reality, whatever input we are providing to the system or aircraft, we are also collecting the response against these inputs. So this is one of the method which is preferred. And in this presentation also, we will focus our attention on flight test methods. Okay, now after choosing this, so what are the methods actually to follow? So in last 6 to 7 decades, we have enormous amount of work in this direction. So if you see, we have lots of methods in frequency domain, time domain. We have methods from tradition. We have approaches in traditional directions, and also novel methods like machine learning based parameter estimation and data driven. So as I said, we have methods in time domain and frequency domain. It's very hard actually to which domain to focus on at the initial stage. So I personally give weightage to both the domains actually, as discussed by the experts in those fields. So the comment by Turkey and Usai in 1998, they say the result shows the superiority of frequency domain parameter estimates in the presence of runout noise. However, frequency domain approach requires an FFT and may be suitable in offline estimation or online estimation of process with flow dynamics. So this was the comment actually by Turkey and Olsay. And this is Jetaga's comment actually, who exclusively works on time domain. A flight vehicle is a dynamic system, and since a state space representation in the time domain is closer to physical reality than any of the frequency domain transform techniques, so time domain methodology is preferred. So this is also kind of taking a call for which kind of process we should go for which method. So again, I would restrict our presentation in time domain for today's discussion. And then in time domain also, as I said earlier, we have methods on physics-based model and data-driven model. So physics-based model says that the principle derives from basic understanding of the physics. All the parameters associated to this model will have their physical interpretation. And system representatives usually are in the form of ordinary differential equation or partial differential equation actually. So this is your physics-based model approach. In data-driven model, it's completely a black box kind of approach. That's why it is also known as black box modeling approach. So they deal with cause and effect relationship. It means only they deal with input and output data set. It's easier to derive, and we do not have initial requirement of physical understanding of the system or physical. We do not deal with physical equations to work with the data-driven model or black box model. Right now, under physics-based model, we have certain methods, standard methods. They are known as equation error method, output error method, and filter error method. So we will see one by one actually what are those, and then we will move further. So under equation error method, we have a very powerful or preferred method known as least squares estimation. It is quite a popular approach. I'm sure we all are familiar to this one. It is unbiased, efficient, and consistent estimation. It is said that about least square estimation, and it gives you the one-shot solution. But the drawback is inadequate performance. It has inadequate performance in presence of measurement and process modeling error. When your data is noisy, we generally have this noise in measurement and process, then it might not perform well. So second kind of method is output error method, and one of the example under this category is maximum likelihood estimation based method. It can handle your measurement error and it also deals with optimization schemes. So there you can think of working with Gauss-Newton based optimization, LM optimization, and GA. So these are certain optimization routine which are involved in MLE based estimation. But again, it has inadequate performance in the presence of process noise. It means it will be able to handle measurement error, but not process noise error. The third one under this category are filter error method. It handles both process and measurement noise, and it works well with linear and nonlinear model both. It has faster convergence rate relatively, and it is used in unstable aircraft parameter estimation. And under this category, we have quite popular method, which is based on your Kalman filter and its variants like extended Kalman filter, unextended Kalman filter, and particle filter, etc. So these were the methods which fall under the category of physics-based parameter estimation or physical understanding-based parameter estimation method. Under this, we have, under data-driven model-based parameter estimation, we have three popular method actually. Delta method has been one of the most popular method from last 2 decades. But these are not the only methods under this category, because nowadays we have lots of tools under AI and ML, machine learning. So these are the three methods which I'll be discussing in this presentation. So I kept under that category. They are delta method, and these two methods are also derived from the first one, which are NFIS delta and GPR delta. But apart from these methods, you have enormous amount of methods. Like you can go for fuzzy logic based method, you can go for random forest tree based method, and also various other types of method using CNN and deep neural network. So now we will try to see one by one. So throughout this presentation, I'll be talking about these three methods: delta method, NFIS delta method, and GPR delta method. So let's start with this delta method. So delta method was proposed way back in 1998 by Professor Ghosh, and then that time supervisor Professor I. Singhania, who was also one of the renowned researcher in the domain of aerospace engineering. So the philosophy of delta method deals with the understanding of feed-forward neural network. I'm sure we are familiar with this concept. So as you can see in this slide, I have kept the architecture of FFNN with feed-forward neural network at the corner, which I'm claiming here as a black box model. So under that FFNN, we have three different layers. They are input layers, hidden layers, and output layers. So we know that our input data will deal with these input layers, output data will deal with output layers. So the heart of this concept is hidden layer, where we are trying to capture the complexity of the problem. So based on the complexity of the problem, we choose the number of hidden layers. So judiciously, we can plan for hidden layers and number of neurons in hidden layer. And this is the actual concept here, FFNN. So once you have this network model, when you are able to train the model on the basis of input and output data, then you will get your black box model, right? So this is quite a straightforward process of getting getting trained model of using FFNN. Next thing comes like when we have network model or ANN model, then what? What is the next? What we will do with that? So now delta method comes into the picture. So after deriving this ANN model, which I say black box model, with these three inputs, in this example, I have taken three inputs as alpha, angle of attack, delta E, elevator deflection, and QC by 2B is your normalized pitch rate. CL and CM, they are your lift force coefficient, and CM is your pitching moment coefficient. So after getting this model, we perturb the variables in both the direction. We add in this variable, for example, alpha, we will add delta of that variable, delta of alpha, and we will perturb the model and we will note down what happens to CL and CM. So let's say after positive perturbation, they give you the output as CL plus and CM plus. And after giving the negative perturbation, they give you CL minus and CM minus. So this is a perturbation in both the direction. And please note that when I'm changing alpha, that time we are not changing these two variables, which are delta E and QC by 2B in this case also. So you might ask the question that why are we doing that? I mean, what's the point of perturbing the model in both the direction? So the answer lies in the physics of these parameters. So for example, when I say CL alpha, this aerodynamic parameter. So what is the physical understanding behind it? So the CL alpha will be change in lift force coefficient for change in angle of attack. So you can see here, so CL can also be written as CL plus minus CL minus by twice of delta alpha. Why twice of delta alpha? Because we are perturbing in both the direction. So effective change will be 2 times delta alpha if we are trying to find CL alpha. And CL alpha plus and CL alpha minus, they are the output of positive and negative perturbation. So by that you will be able to find CL alpha. Similarly, if you want to find CM alpha, we will do the same exercise for this. So I mean, we will note down CM plus and CM minus. We'll take the difference and we will divide by twice of change in alpha, which is your delta alpha. So if I want to find CL delta E, then we will take CL delta E will be equals to again perturbation in elevator for positive direction by keeping alpha and pitch rate constant. Here also perturbing in negative direction by keeping alpha and QC by 2B constant, right? So like that we will get CL delta E and CM delta E. Suppose you want to find CMQ and CLQ. Similarly, we will repeat the exercise for these parameters. So this was the whole understanding of getting these aerodynamic parameters using delta method, and we will see the result. But before we see the result, I would also like to discuss two novel methods recently proposed by me and my professor uh, and also my PhD supervisor, Professor Ajit Ghosh. So we tried in this approach, we tried to replace the understanding of feed-forward neural network with ANFIS, because in ANN what happens? I mean, we all know that ANN is very good for the training, but it lacks the logic. So we know fuzzy logic is known for deriving the logic from the system, and neural network is good for the training of the system. So we thought, like, if we combine both the principles actually, which is a well-known tool nowadays known as neurophagy. So we have taken the advantage of neurophagy and we have put in the delta system or delta philosophy. So ANFIS delta system is essentially a combination of neural network and fuzzy logic understanding. And your feed-forward neural network, which was 3-layer network, is now getting replaced with 5-layer ANFIS architecture. So earlier you have seen input layer, output layer, and hidden layer. Here also we have 5 different layers, and they are following actually. So layer 1, layer 2, layer 3, layer 4, layer 5. So whatever, uh, I mean, we were trying to do the curve fitting with the help of activation function. Now your membership function will get active in this approach. So this was the philosophy of ANFIS delta, and the another one was GPR delta method. So in this approach, we tried to replace the concept of ANN network with GPR understanding, which is your Gaussian process regression model. So under this, this is stochastic. It works in stochastic framework, and we do not have to deal with the layers. So we will also see some of the features of Gaussian process regression. So it's known as powerful non-parametric tool for learning regression. And of course, they come from the understanding of supervised learning based on input-output data set. It's a Bayesian-based approach with a Gaussian probabilistic framework. And GPR accommodates asynchronous data sources, periodic data, missing data, and structured data. I mean, these are the additional advantage of dealing with GPR and other features. So like ANN and ANFIS, we have two different features by which you are trying to, approximate the nonlinearity or trying to capture the dynamics of the problem. They are covariance or kernel function, which gives a method of data, which gives a model of data and control the property of Gaussian process. And another adjustable parameters are known as hyperparameter. By adjusting their parameters, data, you are also trying to adjust the performance of the system. So under these two covariance function and hyperparameters, you will be able to approximate the function. GPR model can model various different traits and properties of a data set. And simple covariance function can be combined to create a more complex one. So I mean, like you can also take a multiple combination of covariance function to derive a GPR function. So these were the understanding of GPR. So under this understanding, we will apply the philosophy of delta method. As I said, if your black box is now GPR model, then again you perturb the system in both the direction and you will get CL alpha, CM alpha, similarly CM delta E and CL delta E, etc. So after knowing the system, we will discuss about the case studies. I mean, now this is time to look for the implementation on of these methods which we have discussed. So to demonstrate these three methods, we have taken three case studies of two different aircrafts. The first one is Hansa 3, which is in-house aircraft at IIT Kanpur in flight laboratory. So we have demonstrated on a lateral directional aerodynamic parameter estimation from simulated noise data. So this is just simulated data and we have added noise purposefully. We will see that how your aerodynamic performance or aerodynamic parameters comes out when you use this data. And second one, to demonstrate the longitudinal dynamics, we have estimated the longitudinal parameter from Hansa 3 flight test data. And then third data is an independent data which were taken from DLR. Reference goes to Dr. Jekatauker. So under this, we also performed longitudinal parameter estimation just to validate our method with another aircraft. Okay. So these are the specifications or technical specification of Hansa 3 aircraft. Length is 7.66 meter, wingspan is 10.47 meter, wing area is 12.47 square meter, and it has maximum takeoff weight at 7.750 kilograms. Cruise speed is around 213 kilometer per hour, and it has a range of 840 kilometer. So to estimate lateral directional parameters, we need to have the flight variables under lateral directional dynamics. So we know that under lateral directional dynamics, we have inputs as side slip angle, roll rate P, yaw rate R, aileron deflection delta A, rudder deflection delta R. And we also tabbed in force and moment coefficient, side force CY, CL is your rolling moment coefficient and CN is your yawing moment coefficient. So you can see the data sample is of 45 seconds. So essentially it's a replicate of one data. So in first data, we have added the noise of 1% and which is your 0 to 15 second. And from again 15 to 30 second data, we have added 5% of the noise. And from 30 to 45%, we have added 7% of random noise. So I mean, just we were trying to elaborate the data. We also wanted to have a bigger data, and purposefully we added the noise of different degrees, just to see that how they respond. And after this training, just I'm showing you only NFIS estimated. Similarly, we also had results for ANN and GPR. So you can see now for, let's say, for example, we talk about CY. So we have definitely trained our model or our FIS fuzzy inference system using 1%, 5%, and 7% of random noise. But for the validation, we have added the noise of different degree in the data, which were not the part of the training. So those data are first adding 3% of the noise data in original signal. And this is the result for CY when we add 3% of the noise data in original signal. And then also we have demonstrated by adding 10% of the noise data. So of course, we can see the interpolation and extrapolation capability of the FIS because these two data were not part of the training. One data was under the dynamics, like within the value of 157, and another 10%. I mean, when I say 10% of the noise data, it is beyond the value of your 7%. So it also gives the it also demonstrates the capability of extrapolation here. Similarly, this exercise was done for rolling moment coefficient CL, and we saw our prediction error in the order of 10 to the power minus 5. This earlier one was for 3%, this is for 10%. And then yawing moment, prediction error again in the range of 10 to the power minus 6 using 3% noise data and 10% of the noise data. So estimated lateral parameters also were compared with the traditional methods, which is here wind tunnel estimation actually. So in the first column, you can see the value of wind tunnel estimated parameters. So few parameters like CLP and CLR, CNP and CNR, they were not taken from the wind tunnel. They were estimated using analytical method, because since being a dynamic derivative, if we do not have a dynamic wind tunnel in static rig, we cannot perform these parameter estimation of dynamic variables. So that's why they were estimated from analytical method. And we saw using NFIS data, delta method and GPR delta method, they were fairly close to the estimated value from wind tunnel. Another exercise we did on the real test data. So earlier I was talking about simulated data. Now we'll be talking about real flight test data, which was again performed on Hansa 3 flight test data. But this time we will be demonstrating on longitudinal parameter estimation or longitudinal dynamics of the aircraft. So under longitudinal dynamics, we have flight variables as alpha, V, and delta E. But yeah, just to show you how flight data is gathered on the aircraft. So these are the flight variables alpha, beta, V, phi, theta, psi, and delta E. So this is the actual flight test data which was gathered on Hansa 3 aircraft. But after getting the data from the flight test, we also need to validate the data, and this process is known as either kinematic consistency check or flight path reconstruction. Sometimes we also call data compatibility check. So data compatibility check must be performed when we work with flight test data, just to assure the data, because data driven modeling is all about your data. If your data are accurate, then there are chances that you will get an accurate model. So we ensure that flight test data whichever gathered, they are compatible for further processing. So this is an exercise of data compatibility check for Hansa 3 flight data. Now we also tried different approach. We have 3 sets of data for this. So first set of data we use for the training. As you can see here, we tag them as FTD1. FTD1 is used for modeling, essentially training, ANN and NFIS modeling, and then FTD2 we used for the validation. So we have validated the data using FTD2, second flight test data, and third flight test data, which is your FTD3. So first flight test data was used for deriving the model, and these two data, FTD2 and 3, were used for the validation. And once we have performed this flight path reconstruction or data compatibility check, then we have to segregate the data in terms of input and output data. So input data here we have kept as, again, same thing, delta E, which is your control surface deflection, elevator deflection, and QC by 2 is your normalized pitch rate and your angle of attack. CM is pitching moment coefficient, CL is your lift force coefficient, right? So now you can see the first 2 is your output data set, and these 3, they are input data set. So once we have input output data set, then we are ready with your implementing this new algorithm. But immediately your question should arise that how do you measure these 2 variables? Because it is quite understandable that in normal flight we have process of recording these data. Angle of attack can be found, or angle of attack data can be recorded, Q can be recorded, delta E can be recorded. But how can we measure in flight these 2 variables? So do we have any sensors which can directly measure CL and CM? So if you have such kind of question in your mind, then you will get the answer with this explanation. So normally what happens, most of the time, most of the sensors which measure the data, they are in body frame, actually body reference frame. So we of course have measurement on acceleration in x direction. We have the thrust data. We also know the thrust inclination angle sigma t. We know the mass or weight of the aircraft. And we also know about the dynamic pressure. We know the surface area of the aircraft. So when we have these physical variables, either coming from the flight test or from the geometrical detail, then we will be knowing about Cx, right? So we will get Cx and Cz, they are your uh, force and moment coefficient body frame. And we know CLCD, they are in your wind frame. So there is a method by which you can transform or convert your body frame force and moments in your wind frame, CL, CD, and CM. So with this, because we know alpha, we now know CZ and CX. So by knowing CX, CZ, and also with respect to alpha, we can get CL and CD. So that is how we get CL, CD, and CM from flight test data. So of course, they are derived from flight variables. So whatever terms here are appearing, they definitely are coming from either flight test data or geometrical detail of the aircraft. So here also you can see P square, R square. We also have the information on inertia. So everything you will get from the flight test data or geometrical detail of the aircraft. Yeah, coming to the estimation part, when we perform the parameter estimation, actual algorithm on this data. So this is the result after employing FTD, flight test data too. So we also kept the result from traditional methods like LS, least squares, and maximum likelihood estimation method. So this is the result of delta method, NFIS, and GPR delta. So I have kept the results only for the strong parameters. They are CL alpha, CLQ, CL delta E, CM alpha, CMQ, and CM delta E. So the results derived from delta and NFIS delta and GPR delta, they are also quite comparable since we are dealing with the real-time data. So what happens actually, you might not get the exactly similar parameters, but they are quite comparable to each other. And we also kept LS and MLE for the reference. And numbers inside the bracket, for example, here, which I have tagged as A, they represent the CR bound. So this is CR bound on MLE, maximum likely parameter estimation, and B is your standard deviation. So these other numbers which are inside the bracket, they represent the relative standard deviation. So using flight test data 3, these parameters again, CL alpha, CLQ, CL delta E, CM alpha, CMQ, and CM delta E. And first, second column says the results from LS and MLE. And these three are from delta, NFIS delta, and GPR delta. Now we'll try to understand the statistically what is happening. So in case of delta method using flight test data 2, this is the histogram analysis on the result. So number of occurrence are quite diverse actually. So spread is more in case of delta method, which is classical method or sort of like the first one in under this category. But now you see, interestingly, we were able to minimize the scatterness actually in this method. When I say Anthis delta method, you see the scattering is getting quite less. So the confidence on these estimate will be a little higher than a delta method. So similarly, all for all these parameters, CL alpha, CLQ, CL delta E, and also for moment parameters, CM alpha, CMQ, and CM delta E. So we have very sharp pick in this category of ANSYS. But the same thing we could not get from, GPR delta. Again, we are observing the scatterness like delta method, but of course it is quite comparable with delta method. So we also kept the results under this category. So after that, we took the data of HFB 320, and these are the technical specification of the particular aircraft. And length of this aircraft is 16.61 meter. Wingspan is your 14.48 meter. Wing area is 13.14 square meter. Maximum takeoff is your 9.2 tons roughly. And cruise speed is 825 kilometer per hour. And range is 2,413 kilometer. So with this data, you can see this is your again flight test data, and we have segregated as input output test data. So input data again, angle of attack, normalized pitch rate, and elevated deflection. So now you see that whatever deflection has been performed, your data is also following that. And after that, I also included drag coefficient in this to complete the exercise. So CD is your drag force coefficient, CL is your lift force coefficient, and CM is your pitching moment coefficient. So now we have set of input data and output data. Then we are again ready to implement the algorithm. So now we have the result from delta method, ANFIS delta, and GPR delta method. And we have compared the result of this aircraft with FEM, which is filter error method. So I'm also trying to make sure that we have discussed with the traditional method, it means LS, least squares, maximum likelihood estimation, base parameter estimation, and also filter error method based parameter estimation. So here is your FEM in first column, second delta, NFIS, and GPR. So generally in this particular literature or the research paper, authors have not incorporated or not estimated CDQ and CD delta I, CLQ and CL delta I. That's why they are empty here. But we have compared, of course, the variables which we estimated, and also we estimated these extra variables just to, get the total essence of these parameters. But of course, again, we are mostly concerned with the strong parameters like CL alpha, CM alpha, CMQ, and CM delta E, because they really help us in designing a good control system and characterizing the aircraft performance. So after that, we can conclude that the two novel methods which we discussed here, ANFIS delta and GPR delta methods, were proposed and demonstrated the efficacy on aerodynamic parameter estimation. Results obtained from these two methods were applied in all three different cases. I mean, those cases were lateral directional parameter estimation from Hansa 3 aircraft, longitudinal aerodynamic parameter estimation from Hansa 3 aircraft, and longitudinal parameter estimation again for HAP 320 aircraft. And we also compared with the traditional methods like least squares, maximum likelihood estimation, filter error method, wind tunnel extracted parameters, and we found that they were comparable to the previous methods, old methods. Results also demonstrate the noise resistant capability, because in first case we introduced the noise of different degrees, and we found that it is still able to give the correct parameters even though we make data noisy purposefully. So comparison result established these two novel methods, which are ANFIS delta and GPR delta, as a viable solution to the parameter estimation problem. Of course, we have so many different methods available these days, and we found that these two can also be an alternative to parameter estimation method. So now, if somebody wants to work for aerodynamic estimation, so these could be the extension of the work, because when you assume linear model, or precisely it should be linear parametric model, then I have demonstrated delta method, ANFIS delta, and GPR delta. Of course, you have traditional methods also like LS, MLE, and filter error method. And now the emerging area of machine learning and AI, you can also think of working with nonlinear parameter estimation or nonlinear modeling of aerodynamic forces and moments. So generally what happens most of the time, aircraft spins in a linear regime. So this is also quite intuitive. But what happens, we have a drawback when aircraft enters in a nonlinear regime. I mean, nonlinear regime will happen when angle of attack is more than 12, 13, 14, 15 degrees. I mean, like when it is in the range of 15, 16 degrees, then your aircraft will become unstable, or it will be in the stall regime. So for that, we don't have a very concretized fit-based model. So data-driven model can also be a very, I mean, like it's a candidate solution when your aircraft is entering in nonlinear regime. So one of the exercise can be performed on quasi-steady stall model. And to solve this problem of nonlinear aerodynamic parameter estimation, you can go either for the traditional method like maximum likelihood estimation, or you can look for GPR. You can also look for CART and random forest bagging and boosting. So CART is your classification and regression tree based method. Random forest again has very wide application for nonlinear regression. Bagging boosting similarly also find their application in this kind of application. So after that, I would like to summarize the presentation, what we have learned in this particular lecture. So we were dealing with the problem of aerodynamic parameter estimation using flight test data. So I described what this parameter estimation is about. We have seen some introduction to this problem, and we also discussed the motivation part, why aerodynamic parameter estimation is required. And the third part, we solved the problem actually. We also learned about a few methods that how to solve the problem of aerodynamic parameter estimation. So if you want to refer this work, then these are the textbook. First one, by Jedegawkar, Rao and Morelli. You can refer the literatures. These literatures are listed here. And also you can, if you want to watch video lectures on this particular topic, then the link is given in the slide. So I think with this, I would like to end the presentation. So thank you very much for your attendance and listening me patiently. So yeah, it's over to Professor Rawat. So thank you so much, sir, and it's over to you now.
Thank you, Dr. Jagat. Now discussion is open. Anybody wish to ask the question, please? Any question from the audience side? Okay, Jagat. Dr. Ajit, there's one question. First question is from my side. Can we make the hybrid drone with the fixed
please.
wing as well as the rotor? Dr. Ajit, my voice is clear.
Sir, yeah, could you please repeat? Actually, I lost the connection. Yeah, please tell me, sir.
Actually, is it possible we can make the hybrid drone? Then that means we also have the fixed wing as well as BLDC motor.
Yes, sir, it's quite possible actually. So nowadays the work is going in the direction of VTOL, as you rightly said. So yeah, definitely it can be done.
Okay. So in that particular capability, aerodynamics will be affected or not?
Yes, I think because now your flight regime is also changing, because for some, for some part actually it is now vertical flight. So your flight regime, when flight regime changes, then usually we see there is a difference in the observed parameters. So definitely we need to do the analysis on the parameters when it is flying at the vertical mode, for example, taking off and landing. And again, we have conventional understanding when it is again flying in the fixed wing mode or in cruise mode.
Okay. Any questions from the audience side?
Yes. Jagat here, I have a question.
Yes, please. Yeah.
Thanks for the presentation. So I have a question. So when we are working with this kind of estimation algorithms, have you also explored the domain of, let's say, interval estimations for the flight? Because we are working on parameter estimation, how different is it from the domain of state estimation in application of these algorithms?
Okay, so Dr. Jagat, I think it's a quite intuitive and a very good question. We have extensively also worked in the domain of state estimation. Generally, the understanding of state is such that it varies rapidly with the time or varies with respect to time. Most of the time, the parameters which I was talking today, they are not meant to vary rapidly. So in that sense, I mean, like they are generally fixed for fixed flight regime. So that is where they can be different from state estimation actually.
And one more question regarding this also. So when we are using this, because we are using real-time real flight test data, so are we also looking into the domains of sensor fusion, using multiple sensors to get the information and then doing the system identification part?
Yeah, it's I mean, it's quite intuitive because there are certain times when you also need to verify the flight test variables. So it's a really wise idea when you work in the fusion, because there are some sensors which is your image processing based, and there are some sensors which is your IR based or lidar based. So it's good to have the technique of fusion, and definitely after your MSDF or multiple sensor data fusion, the measured data will be more accurate and it'll be more reliable actually. Yeah.
And could you comment something on the real-time feasibility?
Yes, of course, because now when we are working about the offline parameter estimation, definitely the need of today's industry is real-time estimation. So we are currently working on that direction. So definitely, there are a lot of work which is also heading towards the real-time parameter estimation using either AI or ML-based methods.
Thank you.
Yeah,
Okay, thank you so
Dr.
much.
Ajit, I have a question. So, the
Yes.
so the current parameter estimation, what I saw was related to a bigger aircraft. So, how this can be applied to smaller size UAVs because they may have the sensor limitations, right, to carry angle of attack sensors and all. So, have you
Okay.
had any? Yeah.
Yes, Vishal. So thank you very much for asking a beautiful question, actually, because the theme of this particular STTP is on drones or generally unmanned aerial vehicles. But the idea of, like presenting the work for bigger aircraft was this, because if you remember, I talked about the wind tunnel based estimation. So inside the wind tunnel, we generally don't keep such a bigger aircraft. Again, it is scaled down in terms of smaller aircraft, right, which is also size of unmanned aerial vehicle. So whatever methods and whatever things I've described for fixed wing aircraft, there is no difference when you are working for unmanned aerial vehicle. Yes, I did some work on flying wing, which was an unmanned aerial vehicle or small size of aircraft. And I think the flight variables required to do parameter estimation are not very exhaustive. So definitely these flight variables are, like gathered easily using nowadays DAX data acquisition systems. So I'm sure that you will be able to do such exercise even on smaller aircraft or unmanned aerial vehicle.
Okay. Fine. Yeah. That's all.
Yep. Thank
Sir,
you.
one question. In case the drone is controlled remotely, so then what are the changes we have to do? These are
Dr.
the
Patra,
usually
could I request you to adjust the microphone because your sound is quite low and I'm not able to really hear.
sir, actually I'm talking from mobile. Anyway, sir, my question is that when it is if our system is without what we call that control joystick type of control, if we do convert it to a remote based control, so what are the other changes we need to do? Sir, am I audible?
Sir, your voice is very low.
Uh, so some problem is there for us.
It's better you write your question in your chat box.
Okay, sir, I'm
Dr.
right.
Ajit,
Yes.
is it fine? He can write the question in his chat box.
So, okay, sir, I'm writing in quickly.
Please write the question in the chat box because your voice is very low, difficult to understand. Dr. Ajit, are you here? No. Dr. Ajit? Okay, maybe there is some issue, link issue. You please send your question to me, mail your question to me. I will forward and he will get, yeah, question is there. Dr. Ajit, your voice is clear? Your voice, you are getting my voice?
Sir, this is my Tapas Patra's question. This is my question. So, if you can, I am able very clear about your voice. Only thing, my voice is not clear, but
Yeah, your voice is now better.
clear.
Now it's better. Dr. T.K. Patra, now voice is better. I think some issues is from Ajit connections maybe. Okay, Dr. Patra, you please you mail this particular question to me. I will keep it forward to the Dr. Ajit, okay, and he will get back to you. Is it
Okay,
fine?
sir. Yes, sir.
Okay.
Thank you.
Thank you very much. So this is the end of the second day of our STTP. Now we have shared the feedback link. So please give the feedback for last today's and the yesterday's. Okay, actually earlier I was planned that take your feedback at the end of the STTP, but many of the participants is told, sir, we will maybe skip, we will forget the few of the things. So please give your feedback, and you can also give some kind of the comment if required. So this is all about today. Tomorrow we will start at 10:30. Okay, so we will meet tomorrow morning 10:30. Thank you very much.